Friday. Welcome to TBE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's event will be able to come and watch it. Thank you. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Ms. Patricia will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Hello, everyone. Thank you, Ms. Salazar. Let's see. So this is our last happy math hour for the semester. Can you guys hear me okay? Because I don't have my mic. Thumbs up, thumbs down.
Yes, we can.
Yes.
All right. So we'll get started. So we're going to review for your final exam. So the first question is find any intercepts and test for symmetry. So here we have our equation y equals negative 2x plus 1. So first we'll find the intercepts. So to find the x-intercept, you want to let y equal to 0 and solve for x. So here y is 0, and we're going to subtract the 1 and divide by negative 2. So negative negative will be a positive half. So that's going to be our x coordinate. And then of course our y was 0, so that's our x-intercept. And then the y-intercept is we let x equal 0, so y equals negative 2 times 0 plus 1. So we're gonna go, can we pause? Can you stop the recording really quick? I just saw, okay, never mind, we'll just continue. So we have y is equal to 1. So our y-intercept would be 0, 1. So in order to graph a line, you have learned different methods throughout the semester, but one method is to use the x and y intercept. Okay, so in this situation, we were able to find the x and y intercept. And so if we were to plot those, then this would be our graph here. Okay. To figure out the axis of symmetry, if it has symmetry, we can look at our graph and determine if it has any symmetry. And so in this example, this has no symmetry for the x-axis, y-axis, or the origin. So now we will have our symmetry. We can find it using algebraic ways. So to find the x-axis symmetry, we switch our y to negative. And so here we're going to have y is equal to negative 2x plus 1. This is our original equation. So we're going to replace the y with a negative. Oops. And then we're going to solve for y. So here we replace the y with a negative. So now we have y equals negative 2x minus 1. To determine if there's symmetry on the x-axis, you want to compare your result here with the original equation.
All right, everyone. Sorry about that. We're having a little technical difficulties, but I'll go ahead and continue. Okay, so we saw for the x-intercept, y-intercept. So now we're checking for the x-axis symmetry. So as Ms. Chuka had said, so in order for us to check for x-axis symmetry, we'll replace the y with a negative y and solve for y. Yes, so when we do this, we get this equation y is equal to 2x minus 1, which is not the same as our equation, so it does not have x-axis symmetry. So So now we'll check for the y-axis symmetry. And to check for the y-axis symmetry, now we'll replace the x with a negative x and solve for y. So when we do this, we see that it's also not the same equation as that is given. So it does not have y-axis symmetry. And to check for the origin symmetry, we're going to replace both the x and the y with a negative. And when we do this, we see that it also does not match. So this particular problem has no xy or origin symmetry. Okay. All right, so let's look at this example. Write the standard form of the equation of the circle with the given characteristics. So the characteristics here are center at -4, 2 and a radius of 2. Okay. So we know that the standard form of the equation is given in this form: x minus h squared plus y minus k squared is equal to r squared. Okay, so we know that our center is given by these two variables, the h and k. Our radius is defined by r, which is 2. Okay, so with this information, all we have to do is replace our variables with what we know. So here our h is a -4, so we have x minus a -4. And then we have our k, which is +2, so it's just y minus 2 squared. And our radius again is 2, so that's 2 squared. So we'll go ahead and simplify. So when we simplify, we have x plus 4 squared plus y minus 2 squared is equal to 4. Okay. Hopefully very straightforward, very easy. These questions, again, this review. By now, we're experts on these. So let's look at this example. Write equations of the lines through the given point that are parallel and perpendicular to the given line. So to review, we know that two lines are parallel if they have the same slope, and we know that two lines are perpendicular. I like to call that they have opposite slopes. So let's go through this. All right, so first, we want to find out what the parallel slope is to this given line. So what I do is I take this equation, 8x minus 2y equals to 3, and I'm going to put it into slope-intercept form. By me doing this, solving for y, it's going to allow me to identify its slope. Okay, so when I do this, I'm going to solve for y, and I'm going to get y is equal to a -3/2 plus 4x. So the value here, 4x, the 4 is the m value, or my slope, for my given equation. So my slope is 4. So in order for me to do this, to get the line that is parallel to this equation, it has to have a slope of 4. So what I will do is I'm going to use the slope-intercept formula to get that equation. Because I have the slope, they're giving me a point that I want the line to go through. So for me, this isn't the only way that I can do this, but I like to do it this method. Okay, so let's go ahead and do this. We're going to go ahead and substitute what we know. So we know that our slope is 4, so that's the value for m. Goes right there. The point that it has to go through is the x value of 8. So that goes there. It's the x1. And then my y value 1 goes in my y1 position. So that's y minus 1 is equal to 4 times x minus 8. So now what we need to do is we're going to distribute the 4, because the answer we wanted in slope-intercept form. Okay, so we'll distribute the 4, and we're going to get 4x minus 32 on the right side. Okay, now I'm going to add 1 on both sides. I'm going to add 1 on both sides to solve for the y. And when I do this, I'm going to get y is equal to 4x minus 31. So this line is going to be parallel to my given line because it's going to share the same slope. Okay. All right, now to get the perpendicular line that is or perpendicular line that perpendicular to this given line, okay, we need to find its perpendicular slope. So the way I do this is if my slope is 4, my perpendicular line has to be a negative. It has to be the opposite sign of that. So it's going to be a negative. And what I do is I convert this into a fraction, the 4, so 4 over 1. And the opposite of a fraction is like its reciprocal. So I would take the reciprocal of 4 over 1. That's going to give me 1 over 4. So this value here, negative 1 over 4, is my perpendicular slope. So now, again, I'm going to go ahead and use the slope-intercept formula to get my equation that is perpendicular to this line. And I'm going to do the same thing as I did before. I'm just going to replace what I know. My m is negative 1/4. My x value is 8. My y value is 1. Let's go ahead and distribute that negative 1/4 on the right side. Okay, so negative 1/4 times x is negative 1/4 x. A negative 1/4 times a negative 8. And when I simplify that, okay, there we go. Okay, so when I simplify this, that negative times the negative is a positive. 8 divided by 4 is 2. So we have negative 1/4 x plus 2. Now the last thing I need to do is add 1 on both sides. And when I do this, 2 plus 1 is 3. Okay, so the equation that is perpendicular to this given equation is y is equal to negative 1/4 x plus 3. Okay. All right, let's look at these other examples. Find the following. So they're giving us two functions that have a function that's in color red, which is f of x is equal to 9x plus 1. We have another function here in blue, which is g of x is equal to x squared minus 4. So they want us to do some basic operations with these functions. So let's do A. They want me to evaluate f plus g of x. So basically what this is telling me, what they want me to do is just add function f with function g. I like to rewrite this. This is the book notation, but I like to think of it as this format, that they want me to add function f with function g. So by me having it in this format, all I have to do is just to do the substitution. F of x is 9x plus 1 plus g of x, which is x squared minus 4, and then I'm going to combine my like terms. So the only two terms that I can combine are my constants, the plus 1 and the minus 4, which is going to give me the minus 3. So this is the evaluation of f plus g of x squared plus 9x minus 3. So let's do B. B is just a subtraction now. So I'll rewrite that. F minus g of x, basically what they're telling me is to do f of x minus g of x. So let me just go ahead and replace f of x and g of x with what I know. F of x is 9x plus 1 minus g of x is x squared minus 4. So before I can combine my like terms, I need to distribute that negative sign. So negative times x squared is a negative x squared. A negative times a negative is a positive 4. Now, again, the only two terms that I can combine here are my constants. So the plus 1 plus 4 is going to give me the plus 5. So f minus g of x is equal to minus x squared plus 9x plus 5. Very good. Again, if you all have any questions, please feel free, raise your hand, or if you want to unmute yourself, by all means, please ask. Let's go ahead and do C. C says to evaluate fg of x, okay? So what that means, fg is two terms together, it's multiplication. So I like to rewrite it in this format, f of x times g of x. So then all I have to do is a substitution. F of x is 9x plus 1. G of x is x squared minus 4. For this particular one, I have to do FOIL. Okay, so 9x times x squared is 9x cubed. 9x times a minus 4 is a minus 36x. A plus 1 times x squared is a plus x squared. A plus 1 times a minus 4 is a minus 4. Okay, now you can leave the answer like this because there's no like terms that I can combine, but I like to have things in standard form. So standard form means the exponents are in decreasing order. So you don't have to do this, but I like to rewrite this as 9x cubed plus x squared minus 36x minus 4. I think it just looks nicer this way. Anyway, let's do D. D says f divided by g of x, okay? So basically what they want me to do on this particular problem is just do the division of f of x with g of x. So all I need to do is replace what I know. F of x is 9x plus 1 divided by g of x, which is x squared minus 4. Now this problem, I cannot factor the numerator, I cannot factor the denominator, and they're already, both of those functions are in simplest form. So the answer is just that. F divided by g of x is 9x plus 1 over x squared minus 4. Now let me see if I have it here. Yes, on your homework and probably on your test, one of the things that they're going to ask you to is what is the domain of this division, right? Because what we end up is with a rational function, right? So we never want on a rational function or a fraction example, we don't want the denominator ever to be 0, right? Because we'll get an undefined. So if we don't see it, the way to solve for the domain, what we can do first is set the denominator equal to 0. My denominator here is x squared minus 4 equals to 0. And I'm going to solve for x to see if I have a value that will give me x. So when I do this, I'm going to add 4 on both sides and get x squared is equal to 4. Then I'm going to take the square root of both sides. And I'm going to see that x is equal to plus or minus 2. So these two values I cannot use because I'm going to get a 0 on the denominator. So the domain of this function in interval notation is from negative infinity to negative 2, union negative 2 to 2, union from 2 to infinity. Now, just a quick review, okay? The infinite symbol, since it's not a value, the infinite value goes on. We always use parentheses for the infinity symbol, okay? Now, for the negative 2 and the 2, and we don't want to use those values, but those are our stopping points, right? So we indicate those as parentheses as well, okay? So be careful on that. We are only going to use brackets when we want to include the number in interval notation. All right, so let's look at this graph. It says, does the function have an inverse? So let me take the time to review first what a function is, right? Or how we can determine if what we're looking at is a function. If they give us a graph and they ask us first, is this a function? Well, we all know that there is a test that we can perform to see if this is a function. And that test is called the vertical line test, right? So if we wanted to test that if this graph was a function, we do this imaginary vertical line and we traverse it through our graph. And if we see that our imaginary vertical line only crosses our graph once, then this is a function. So we want inverse function, right? The opposite. So what is opposite of a vertical line? Horizontal line. So if we want to check to see if this graph has an inverse, what we would do is perform a horizontal line test. We do this imaginary horizontal line and traverse it to our graph. And if our imaginary horizontal line only crosses our graph once, then this function has an inverse. So because this graph here, it passes my horizontal line test, then this graph will have an inverse. Okay. Now, so this is what I just talked about. Again, to find out if a graph has an inverse function, you'll perform this horizontal line test, okay? And if it fails, if it fails my horizontal line test, it's not going to have an inverse. All right, so let's look at this problem. Determine whether the function has an inverse. So if it does, then find the inverse. So let's see here. So first of all, it helps to know what type of function it is to see if it has an inverse or not. So we see that this function has a square root. We're evaluating the square root of x minus 8. So this is a square root function, right? Or a root function. So this function will pass the vertical and horizontal line test. Okay, so if we remember the root functions from our parent functions, they're these curves, right? That have a vertical asymptote. So this function will pass our vertical and horizontal line test. So therefore, this function has an inverse. So let's go ahead and calculate it. How can we solve or determine the inverse of a function? So my step to do this is the first thing that I do is I like to convert the function into an equation. Okay, so I'm going to replace the f of x with y. So when I do that, I have an equation. Y is equal to the square root of x minus 8. So since I want the opposite of this function, its inverse, what I'm going to do is I'm going to interchange the x and y values. I'm going to make the x to be y and the y's to be x. So let's go ahead and do that. When I do that, I get this. X is equal to the square root of y minus 8. Now all I need to do is now solve for y. So to get rid of or to get rid of or eliminate the square root, what I'm going to do is I'm going to take the square of both sides. Okay. And when I do that, we like to say that it eliminates. It doesn't really eliminate. The only thing that happens is my exponent becomes 1. But you all know it that we can get rid of our square root, right? So the square root of a square, we get an exponent of 1 or just y minus 8. So x squared is just x squared. Then I'm going to solve for y by adding 8 on both sides. Now we're going to get x squared plus 8 equals y. So the last thing that I need to do to indicate that what I discovered is an inverse, I need to replace now the y with this notation, f to the exponent of negative 1. This symbol here means that is an exponent. So please don't forget to put that on your finals. No, you don't want to lose points for not indicating that we are dealing with an inverse. So the inverse is x squared plus 8. Okay. All right, let's look at another example. It says sketch the graph of the function by applying the leading coefficient test, finding the real zeros of the polynomial, plotting sufficient solution points, and then drawing a continuous curve through the points. So the function that they want us to sketch is this. G of x is equal to negative x squared plus 12x minus 32. Okay, so hopefully we can determine that this is a quadratic equation and the shape that we should sketch is going to be a parabola. Now, let's look at applying the leading coefficient test to give us details as far as how this parabola is going to look, right? So the leading coefficient test tells us how the graph will be behaving, right? So in our particular problem, okay, the leading coefficient of this example is a -1. That's the leading coefficient refers to the coefficient with the variable with the highest exponent. So my highest exponent here is the 2, the square. So its coefficient is that -1. We don't put a 1 there, but we know it's a -1. So the leading coefficient states that if it's a -1 and our function is even, which is in our case our quadratic is an even function, the behavior of my graph is going to be that it's going to fall on the left and fall on the right, right? So if we look at here our examples, the answer would be this last one. The graph of the function falls to the left and falls to the right, okay? So, and let's do a quick review since we are reviewing for our final, okay? Let's go through some of the characteristics of the leading coefficient test. So the leading coefficient, if your coefficient is negative and your function is even, is what I just explained to you here, that the graph is going to fall on the left and fall on the right. Now, if my leading coefficient would have been a positive, because the graph is even, it would have rised on the left and rised on the right. Now let's say that they would have given me an odd function, okay, and the leading coefficient was positive, then it was going to fall on the left, rise on the right. If the leading coefficient would have been negative and an odd function, it would have rise on the left, fall on the right. Okay, so this is just a review for your final. So now that we know the answer, or we know the behavior of this graph, let's find the real zeros of the polynomial. Okay, so since we have a quadratic, there's several ways of doing this. See, everything that I just explained, and here's the graphic representation of what I just went through. Okay, so since I already said it, let me go ahead, and we know that our graph is going to fall on the right and fall on the left. Okay, now we're here now, the B part. So since we have a quadratic, there's several ways to do this. We can factor this, we can complete the square, we can use a quadratic equation. So let's see here. I like to always try to factor because that's my go-to. I think it's the simplest way. So, and that's what I did here. So I'm going to factor this minus x squared plus 12x minus 32. And the way I factor this term is I say to myself, I need to find two terms that will give me the c value and they add up to the b value. So I have here x minus 8 times x minus 4. So when I multiply these two values, this is going to give me the 0 value, right? So the only way that I can get 0 here with this product is if either x minus 8 is equal to 0 or x minus 4 is equal to 0. So if we don't see it, we can do the algebra to solve for the x. Here in this first one, x is equal to 8. If I plug in 8 to my polynomial, this is going to give me a 0. And if I add 4 on both sides here, x is equal to 4. So if I plug in 4 as well, it'll give me a 0 on my polynomial. So these are my zeros for my polynomial. So these are, it's telling me where it's going to cross the x-axis. Okay. Now, we could also, I found where it crosses the x-axis. We can also find where it crosses the y-axis. So to find the y-intercept, this one's the easier one. We can just replace x with 0. So everywhere we see x, we're going to plug in 0. So 0 squared is 0, 0 times the negative is 0, 0 times 12 is 0. So 0 minus 32 is a negative 32. So my y-intercept is negative 32. Now we can also use some formulas that we went over in chapter 2 to find the vertex. Since they gave me a polynomial in what's called, I guess, general notation, where we have ax squared plus bx plus c, we can use this formula to find the x value of the vertex, which would be given by negative b over 2a. And to get the y value of the vertex, we just plug that value into the function to get our y value. So let's go ahead and do this. In my polynomial here, my b value is 12. My a value is the negative 1. So I'll replace this here. 12 divided by 2 over negative 1. And again, there's a minus there in front of it. So 2 times the negative 1 is a negative 2. 12 divided by a negative 2 is a negative 6, and the negative 6 times the negative sign will give me that positive 6. So this is the x value of the vertex. To get the y value of the vertex, I'm just going to plug it back into the given function. So here, everywhere I see x, I'm going to plug in the 6. So we have 6 squared. I'm sorry, 36 times 6 is 36. 36 times a negative is a negative 36. We have 12 times 6, which is 72. And then minus the 32 is going to give me 4. So the vertex here is 6, 4. Okay. So now we have all these points that we can plot into our graph. Again, these were my x-intercepts, the 4 and 8. Again, we can see the y-intercept, which is way down here, the negative 32. Okay, but we can do several points again to get this smooth curve. Okay, and this is what we said about additional points to get a better idea of our graph. Okay, and the fact that we know that our behavior from our leading coefficient test that the graph is going to fall on the right and left gives us our parabola. All right, so let's use the rational zeros to find these polynomials. So let's start with the rational zero test. Okay, so the rational zero test, again, this is a test. This is to find the possible zeros that one can have, right? So a test, like when we were in COVID, right? We can either get a positive or a negative. And we always wanted the negative in that case, right? We never wanted to be positive for COVID, right? But same thing with this test. This test will either give us the zeros or it might not give us the zeros, but it's a way to find possible zeros. So the rational zero test says this. We take the factors of our constant term, which in this case is 9. I'm not interested in the sign because I'm going to get all of the positive and negative values. Okay, so I'll get all the factors of my constant, and I'm going to divide them by all the factors of my leading coefficient. So in my example, I have a 1 here. So the factors of 9 are 1, 3, and 9. And like I mentioned to you, I don't care that it was a negative 9 because I'm going to look at all of the signs. So it's going to be plus or minus 1, plus or minus 3, plus or minus 9. And for the factors of my leading coefficient, it was just a 1. So it's just a plus or minus 1. So when I do the division of this, plus or minus 1 divided by plus or minus 1, plus or minus 3 divided by plus or minus 1, plus or minus 9 divided by plus or minus 1 gives me these possible zeros. And if you're doing a test, if your class is online and you're doing inputting them into the system, there is no plus or minus symbol on WebAssign, okay? So it wants you to put them as a list. It wants you to put them like -9, comma, -3, comma, -1, comma, 1, comma, 3, comma, 9. Yes? So there's no symbol for plus or minus. So why is this useful? Well, if we're trying to find the zeros of this polynomial, we don't want to try infinite number of solutions because we can basically pick any values to see if they're a zero, but we don't want to do that, right? We want to give ourselves better chances. So here, by using the rational zero test, it gives me just 6 values to test, and hopefully one of these will result to 0, okay? Or it might give us all of the zeros, right? So since this is a polynomial of degree 3, this polynomial technically should have possibly at most 3 zeros, right? And true zeros. So let's look at this. So if I want to find the zeros, I'm going to use the possible zeros that I found, and I'm going to use synthetic division to see if I can find a zero. And synthetic division, I love it because it's a quick way to see if one is a zero of the polynomial. It becomes a factor of the polynomial. So let's go ahead and do synthetic division. So a quick reminder also of synthetic division. When you're going to do synthetic division, you're only going to grab the coefficients of the polynomial, but you got to make sure that there is a placement value for the polynomial and that the polynomial is in descending order. So here I have a polynomial of degree 3. So I should have a placement value for a 2, a 1, and a constant, which I do, and the polynomial is already in descending order. So I can just grab the coefficients. Let's go ahead and put them. My coefficients are 1, 1, -9, and -9. So the way I do synthetic division, the first thing I do is I bring down my 1, and I'm going to multiply this 1 times 1. So 1 times 1 is 1, and then I'm going to add these two terms. 1 plus 1 is 2. Then I do it again. 1 times 2 is 2, and then I'm going to add these two terms. -9 plus 2 is a -7. And then I'm going to multiply 1 times -7. It's going to give me a -7. And -9 plus -7 is a -16. So since the remainder here, always your last value is our remainder of our of our division. Since this value was not 0, then 1 is not a 0 of this polynomial. So let's go ahead and try another of our um, examples. So we have also the -1. Let's try our -1. Again, I'm going to do the synthetic division, bring down my 1. -1 times 1 is a -1. 1 minus 1 is 0. -1 times 0 is 0. -9 plus 0 is -9. -1 times a -9 is a +9. And -9 plus 0 is 0. Awesome. This makes me happy because when I just found out that when x is equal to -1, this will give me a 0. Now, so I have 1 in the zeros already, -1. And if we see here, the the quotient here that we have left, I can rewrite it as a function. There was Keep in mind when you're dividing, you're going to lose a degree of your polynomial. Since my polynomial started with a degree 3, my quotient is going to have 1 less. So the first term here, there's only a 1, but this is going to be an x squared. I have a 0 for x, so, and then my -9 is my constant term, so it's -9. Again, I had no remainder. So this quotient here is an x squared. So now actually I can solve for the remaining zeros. So one of the things that I can do is I can go ahead and use my square root property to solve for the remaining zeros. So I'll first do is add 9 on both sides, okay? And then I take the square root of both sides. And when I do that, I'll have the square root of 9. Again, the square root will give me two answers, a plus or minus. So the square root of 9 is plus or minus 3. Voila, I've got all my zeros. I have a -1, a +3, and a -3. These are my zeros of my graph um, here. So now I can graph the polynomial, right? So let's go ahead and do it. Let's plot our zeros first. So I had a 0 at -1, a 0 at -3, and a 0 at 3, which are here my green dots. All right, so now let's use our end behavior that we reviewed already. We have an odd polynomial, okay? So because it's a degree 3, 3 is an odd number, it's an odd polynomial. My leading coefficient is a positive value. So for an odd polynomial with a positive leading coefficient, it's going to fall on the left, rise on the right. So this is what's happening in blue, right? These are my lines. I know what's going to happen. But let's see, how can we determine what's happening in the middle here between these two? So the best way to do this is to just plot some points to see what's happening. So here, I want to pick a point that's between -3 and -1. So I picked -2 to find out what's happening in here, right? So when I plug in, when x is a -2, my y value is 5. Okay, and then I like to pick another point between -1 and -3. So what I did is I picked 2, positive 2. So when x is equal to 2 and I plugged it into my polynomial, I got a y value of -6. And just to be a little bit more specific, I picked 1. Let's see what's happening at 1. So when x is equal to 1, I got a y value of -16. So with these points, I can plot them, okay? And I'll try to attempt to do the smooth curve, right? So voila. You use all these methods to graph a polynomial. Find the zeros, know its end behavior, and sometimes it'll require us to do a little additional points. Okay. All right, let's look at another example taken straight off from your homework. Use the given zeros to find all the zeros of the polynomial. Okay, so they're giving me this polynomial of degree 3, x cubed minus 12x squared plus 5x minus 80. And they're telling me that I have a zero of this complex term now, 4 plus 2y. So believe it or not, we can also use synthetic division to simplify polynomials, and we can do it in this format. Again, my 0 is 4 plus 2i. Let's look at my polynomial. It's a degree 3. Do I have a placement for all? Yes. 3, 2, 1 constant, and it's in order. It's in descending order. So let me just grab my coefficients. I have a 1, negative 12, positive 52, negative 80. All right, let's go through this. First thing is I need to multiply 4 plus 2i times 1. That's going to give me 4 plus 2i. Okay, I don't have an imaginary number for the negative 12, so I'm just going to add this. And this is a good practice for adding and subtracting imaginary numbers and having them in standard form. A complex number in standard form is always real plus imaginary. So here I have the real part is negative 12. I'm going to add it to the real part of the complex number, which is a 4. So negative 12 plus 4 is a negative 8. There's no imaginary number for the top, so it's just plus 12i. I'm going to do that again. I am going to multiply 4 plus 2i times a negative 8 plus 2i. Again, we will do FOIL for this, okay, which is going to give me negative 32 plus 8i minus 16i plus 4i squared. We can combine our like terms. We can add the 8i minus 16i, which is going to give me 8i. Now, also keep in mind, I squared. This value refers to negative 1. Every time you see I squared, that is defined by negative 1. So I can replace it, and it's going to give me the negative 4. So now I can add this constant, negative 4, with that negative 32, which is going to give me negative 36, right? So that's negative 36 minus 8i. Now I can go ahead and add these two numbers now. Again, I'm only going to be able to add real with real. So 52 minus 36 is 16 minus the 8i. I am going to do it again. I'm going to multiply these two complex numbers, do FOIL. I'm going to get 64 minus 32i plus 32i minus 16i squared. And when I simplify, I get 64 minus 16i squared, which, again, I squared is negative 1. So negative 16 times a negative 1, it's going to give me a positive 16. 16 plus 64 is going to give me the 80. So negative 80 times 80 is 0. Okay, so what I did here is just to confirm that this was a 0, but I used it to reduce my cubic into a quadratic, right? So I have my quadratic, which still has complex numbers, so this is still a little bit messy, right? So what I can do is I can do it again. Let me go ahead and use synthetic division now with my quotient to if I can simplify it even further. So again, I'm going to go through this kind of quickly because this is just review now. And when I do this, I get a remainder of 0. So now my quotient is just x minus 4. So I can find the remaining zeros just by setting this equal to 0. So I know that x minus 4 is going to give me a 0 at 4. So now I have my answers. My zeros are at 0, sorry, at 4. This should be 4, not 0. At 4, and we have a plus 2i and a 4 minus 2i. So again, this is a cube function. These are my zeros. I only had one true 0 at x equals 4, and I had two complex zeros. So 4 plus 2i. Again, remember, the complex numbers come from taking the square root of a negative number. So we always have that plus or minus. So that's where that minus 4 minus 2y came from. Okay. All right, let's consider this rational expression. So first, they're asking us state the domain of the function. Again, we covered this already. We never want functions, rational functions or fraction functions to have a value of 0 in that denominator. So if we don't see it, we can set it equal to 0. X plus 3 is equal to 0. And we will see that we'll get a 0 down there if x is equal to negative 3, right? So x cannot be negative 3. So our answer here, well, if you don't see it, x plus 3 set it equal to 0, you'll see that x is equal to negative 3. So the answer for us is going to be all real numbers except when x is equal to -3. It's going to be that last option, right? All right, so this will be the exclusion for our domain. Now, let's find the x-intercepts. To find the x-intercepts, we set y equal to 0 and solve for x. So let's go ahead and do that. Let's replace that x with 0. So we're going to have 0 plus 3. I'm sorry, 0 is equal to 1 over x plus 3. Now we need to multiply x plus 3 on both sides. And what we're going to notice is we're going to get a non-valid equation. Here the x plus 3 become 1, and 0 times x plus 3 is 0. So this is not a true statement. 0 is not equal to 1. So what this is telling me that it has no x-intercepts. Okay, they don't exist. We would put, if you had again an online class, you would put for the x-intercepts, DNE does not exist. Okay, now if I want to find the y-intercepts, I just set x equal to 0 and now solve for y. So here I replace x with 0, so we have 1 over 0 plus 3. We simplify, we will get 1 over 3. So our y-intercept in as a point, x is equal to 0, our y is 1 over 3. Okay. All right, now let's find any vertical or horizontal asymptotes. So first, there's some so for the vertical asymptote, it's going to be easy, okay? And it's a process that we already did. Any vertical asymptotes is any restriction on our domain. So we saw that when we wanted to find the domain of this function, we set our denominator equal to 0, and we found that when x is equal to -3, this value was a restriction. We cannot use it because it was going to give us a 0. But we actually also found out is that x equals -3. Since this is the restriction, this is the equation of our vertical asymptote. Okay, so this equation has a vertical asymptote at -3. Now, what is a vertical asymptote? Again, a vertical asymptote or a horizontal asymptote are these imaginary boundary lines that our graphs have that cannot be crossed or touched. Okay, so this is this vertical line here indicated as a dashed, right, in red. Okay. Now, for our horizontal asymptotes, it asks us also for the horizontal asymptotes. For horizontal asymptotes, we have several cases, which these are our 3 cases. Given a polynomial, if the degree of the numerator is smaller than the degree of the denominator, then we'll always have a horizontal asymptote at y equals 0. Our second case is if the degree of the numerator is equal to the degree of the denominator, we will have a ratio for a horizontal asymptote. And our ratio would be given by this. Y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then the last case, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. But what this one is going to indicate that we're going to have a slant asymptote. But as far as a horizontal, we won't have any. If your problem asks if it has a horizontal asymptote. So on our particular one, we can see that our degree of our numerator is smaller than the degree of the denominator. Now, if you're a little not sure, what I can replace my numerator is by x to the 0 power. Anything to the 0 power is going to give me 1. So I can say that my numerator has a degree of 0, and the degree of my denominator, we don't write it here, but there's a 1. So that's why the degree of my numerator is smaller than the degree of my denominator. So this particular problem is going to have a horizontal asymptote as the first case at y equals 0, indicated here as a dashed line in blue. Okay. So now that we have our vertical and horizontal asymptotes, we can graph this. This is what we know. It has no x-intercepts. It has a y-intercept, our horizontal asymptotes. So to get a better idea, let's plot some additional points. Okay, so my additional points that I'm picking is at -2 and 2. When I plug in x equals -2, I get a y value of 1. When I plug in x for 2, I get a y value of 1/5. Okay, so this doesn't really help me a lot. So let me pick a few more points. Let's pick x at -4. Gives me a y value of -1. When x is equal to -5, I get a y value of -1/2. So this will help me out to get a better idea of what the graph looks like. Okay, so these are my points that I just plotted, my extra points, and I'm going to attempt to draw smooth curves based on what I know. But again, I'm not going to do that with my pen. I use the computer for it to plot it for me. So remember, the asymptotes come very, very close to our graph. We're not allowed to cross it or touch it. We come close to these lines. Same thing on the right side. They are very close to my vertical asymptote, and then they get close to my horizontal asymptote at y equals 0. So this is my graph of this function. Okay. Now, if you are doing homework or probably on your final, if you have a online class, they're gonna give you, once you plotted this, it's a multiple choice problem, and you're just gonna match your graph with what's given, right? So if we see here, the answer that we're looking at looks like it's this A one, right? Because this is my x and y axis. This is the only graph that has the graphs to the left of the y-axis. So again, it's our first answer. And they're that easy, you know. If you've done your graph, an estimation, you don't have to be so exact. You can easily point out your solution. Okay. All right. Let's look at another example since we're reviewing for finals. Let's use properties of logs to expand an expression. So we have this problem, okay, one of our most popular problems. We have the log of base 5 of the square root of x squared minus 9 divided by 4. Okay, so to expand this, the first thing that I'm going to see here, this input value into my log, I see a quotient, or I see two things dividing, right? So I'm going to use or apply my quotient rule. My quotient rule says that when I have a log of a given base and its input is, I have an input value that has a division, I can expand it by subtracting, right? So I can have two logs now. I have the log of base 5 of the square root of x squared minus 9 minus the log of base 5 of 4. I just subtracted the numerator with the denominator. All right. So now what I see here is that I have an exponent value for the first part. Okay. So I see here that I can rewrite the square root as an exponent, and we know hopefully by now that the square root can be written as x squared minus 9 to the 1/2 power. And by me having an exponent, what this tells me is now I have a power rule, okay? That in the power rule says this, that when I have an exponent, I'm going to multiply that exponent to my log. So since I have an exponent of 1/2, I'm going to multiply it to my log, which is 1/2 log of base 5. And I'm going to have x squared minus 4. Now, be careful, because sometimes you can also write this as an exponent. The 4 can be 2 squared. But on some of the homework, the computer missed that. Okay, so and I think this is the example that we covered. It missed that power, but it's okay. All right, so now you might think, oh, we're done. No. Here, this input, x squared minus 9, I can rewrite that because this guy is factorable. What I see here is a difference of squares. Okay, so this x squared minus 9, I could have rewritten this as x squared minus 3 squared. So when I have a difference of squares, that means that I have x minus 3 times x plus 3. So now what I see here, to a given log, I see its input has two things that are being multiplied to each other. So then what that means is I can apply my product rule. So my product rule, as the opposite to the quotient rule, when I have two things being divided, now I have two things being multiplied, I am going to have a summation of logs. Okay, so I can expand this log of base 5 of x minus 3 times x plus 3 to, let's not forget the 1/2, okay? So we have the 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus log of base 5 of 4. So what expansion means is you're going to take a single log expression and you're going to put it into multiple logs. I went from 1 log to 3 logs. Okay, so this is what expansion means. Okay, so now let's do the opposite. Let's do condensing of expressions. We'll do the A1 and then we'll kind of skip the B just for time purposes. So again, we want to go from multiple logs to just 1 log. So let's go ahead and do A. A has log. So another thing. Do you see that this says that there's no base, there's no number here, no subscript. But when they don't write a subscript, that means that it's a base 10. Okay, so these are all the same logs. Now keep in mind, in order for us to use our properties of logs or to be able to condense, they all have to have the same base. So since all of these logs are of base 10, I can apply my properties. All right, so since there's no parentheses telling me order of operation, I'm just going to take this guy from left to right. Okay, so I'm going to start with this log of x minus 6 log of y. But before I do that, I just noticed something. I see that I have a number being multiplied to the log, so I have to follow order of operations here too. So when I have a number being multiplied to the log, that's the power rule. That comes from an exponent. So let's do that first. I have here the 6 times the log of y. That becomes log of y to the 6th power. I have a 7 being multiplied to the log, so I have a log of z to the 7th power. So now that I took care of that, now I'm going to go just from left to right. I have log of x minus the log of y. To combine these, I'm going to apply my quotient rule that says when I have two logs that are being subtracted from each other, I can divide the inputs. So that's going to condense to just 1 log, log of base 10 of x divided by y of 6. Then I have plus the log of base 10 of z to the 7. Oh, now I have two logs that are being added to each other. This is the product rule. So I'm going to apply the product rule that says that I multiply those inputs, right? So I am going to have the log of base 10 of x over y to the 6 times z to the 7. And I'm going to simplify that. And I'm just going to multiply that to the numerator, right? I can convert the z to the 7 to z to the 7th over 1. And the way we multiply is just straight across, which is going to give me my final answer. The log of base 10 of xz to the 7th over y to the 6th. Okay. Again, let me just skip the B because it's basically the same. Again, keep in mind that you can download this PowerPoint presentation by using the little arrow with the box. Okay. So let's see if I can get to just the last example that we have here. Here, let's do this one. I'll do this one as my last one. That has a little bit of a calculator feature to it. So we want to condense, right? So we want to solve the logarithmic expression, and to do this, to solve it, we want to condense it, right? We want to be able to solve for one value. So here, I see here on the left side of the equation, I have two logs. These are the business logs or the natural logs. And so they're the same base and they're being subtracted. So I apply the quotient property, which is going to give me the natural log of x divided by x plus 6 equals to 7. So what I can do, I'm going to convert it into a log. That way I can see its base, right? So the log of the natural log, if I convert it to a algebraic log, so we have the log of base e of my input x over x plus 6 is equal to 7. Now the reason why I did this is because as we can see, it's very hard to solve for logs, but it's very easy to evaluate exponential expressions. So this is a good way also to practice converting a log to an exponential expression. So here, I have a log of base e. So the base of the log is also the base of the exponent. So I have a base e. The input of a log is the output of an exponential expression, which is going to be x over x plus 6. And the output of the log is the input of the exponential expression. Okay, so now this is very easy to put in my calculator. E to the 7 will give me a value, but I'm not going to put it in yet because I want to solve for x. Okay, so I'm going to do a little algebra. I'm going to multiply both sides by x plus 6, distribute, factor out the x, and I get this value. Okay, so again, I did run out of time. I want to thank you all for joining us. This was our last Happy Math Hour for this semester. We will be back in the summer and in the fall for you. So please take care, study hard for those finals. You guys will all do great. Thank you for joining us.
Yes, thank you. Thank you. If you would like to download a copy of the presentation, again, you can go to the top right corner and click on the box with the arrow going down. We have a little blue arrow on the screen where it'll show you where. We do want to remind you all that we have our previously recorded sessions, which are available on our YouTube playlist. This session will also be available on that playlist later today. We also linked a short survey to help us improve our TVE sessions. If you could just please take a few minutes to fill out that survey and remember to send us your student ID number. Before we end the session, I want to share the last TVE session that we will have for spring 2023. Okay, there we go. So at 1 p.m. today, we will have a presentation. Okay, there we go. So at 1 p.m. today, we will have a presentation of summer camps for kids and library resources. Today was our last Happy Math Hour for the semester, so we want to wish everyone good luck on finals, and we hope to see everyone again for the Hennel virtual event. Thank you all, and again, good luck. We hope everyone has a restful weekend and a successful finals week. Thank you, everybody.